So we'll talk about compactness of sets, we'll talk about compactness of operators, and we'll define one or two auxiliary concepts like what we mean by a finite rank operator. And then I want to do an example to illustrate some of these ideas. And the example that we'll use is one of integral operators, and integral operators are integrals that act on a function. So we'll say an operator is an integral operator if it defines an integral equation. Come back and say lots more about this when we talk about when we get into integral equations and integral operators a little bit later. But now it will be a first example that I want to make some points around. So to start off, let's recall some ideas of analysis. Because I'm not sure where I go with the calculus. And the first one that we need is the Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem tells us that a subset of R to the n is compact if and only if it is closed and it is bounded. So compact subset of R to the n is compact but only if it is closed in the sense that we've already defined and bounded in the sense that we've already defined. A corollary of this is then is that the spectrum of a bounded linear operator is a compact subset of the set of complex numbers. So we know already from things we've said earlier that the spectrum if A is a bounded linear operator in Hilbert space H, then the spectrum of A is closed and bounded under the identification of set of complex numbers as the real two plane, with the real two plane, right? So I can write every complex number as x plus r1. So this necessarily implies that the spectrum of any bounded linear operator on a Hilbert space is a compact subset of C. Okay. So we now spent a bit of part of the lecture, a bit, just devoted to setting up lots and lots of formal definitions. What I'm going to do today, mostly, is to see how we use these formal definitions to understand compact operators and their spectra. The reason I want to do this is because this really is a course in applied operator methods. So we're looking to apply these ideas to some specific physical pictures. And the physical picture that I have in mind, for the most part, is quantum mechanics. I want to convince all of you guys whether or not you've done physics is kind of relevant. Quantum mechanics, as studied by John von Neumann, is basically a theory about operators and their spectrum. Specifically compact operators. Okay. So I'm going to start then with the following observation. So suppose that I've got a compact set so suppose I've got some compact set K, some compact subset in H1. And a continuous map between H1 and another Hilbert space H2. Then the statement is that F acting on all of K is compact. In the Hilbert space H2. And since all bounded operators are continuous, this necessarily also means that all bounded operators map compact subsets to compact subsets. This then allows us to define what a compact operator is. So an operator A and set of bounded an operator K from H1 to H2 is called a bounded operator if it maps a bounded subset of H1 into a bounded subset of H2, or at least a subset of H2 that has a compact closure. The definition is that while it's technically correct, it's operationally very hard to work with. So if I give you some operator and I want to know whether this operator is sorry, the operator is not bounded in you, so there's some these compact. Okay. So if I give you an operator, some bounded operator that takes me between H1 and H2, and I want to know whether this operator is compact, then you have to check specifically that it maps bounded subsets of H1 into subsets of H2 with compact closure. Right? We would like a more operationally useful definition. So to that end, let me give you another definition, which probably doesn't sound more useful, but it turns out it is. Alternatively, A in B between 1 to H2 is called compact, because it only is. For every any bounded sequence of vectors in H1, the sequence that I get when I act on these vectors with K produces another sequence in H2, and this sequence is a let me rephrase that. So come back if I only have so any bounded sequence of vectors X in H1, the sequence that I get by acting on the pieces of K has a convergent subsequence in H2. I'll explore this in some examples. Suppose then I have a set of bounded operators of some Hilbert space in H. So consider of bounded operators. H. If K is a bounded operator, sorry, if K is a compact operator, and another operator T is bounded, so I've got a compact operator B, compact operator K, and a bounded operator T. Then following these two. The composite operators T, K, and KT are both compact. So these are the operators that I get when I act first with T and then K. Remember, K is compact, T is bounded. And their composition are both compact. See why? Note that if Xn is a bounded sequence, then so is the sequence that I get by acting on this sequence with a bounded operator T, by definition of what it means to be a bounded operator T. Let's call this guy to define the sequence Yn. Okay, so the Yn is a sequence of vectors that live in H2 that I get by taking the sequence that I started off in H1 and acting on each of them with the bounded operator T. Statement then is that if this is a bounded sequence, so is this sequence. But we also know that K is compact. So since K is compact, this also means that the set of vectors K acting on the Y-end is KT acting on the X-end must have a compact subsequence. necessarily means that KT then must be compact. On the other hand, the compact operator K maps bounded sets onto compact sets. So K maps bounded sets compact sets. And T, which is a bounded operator, then maps onto compact sets. So T is a bounded operator, and T maps compact sets to compact sets. So T, K, then maps bounded sets to compact sets. And hence K also is compact. A special case of this particular example of the composition of compact and bounded operators is that if I have the product of two compact operators, they must automatically be compact as well. And so the product follows that product of compact operators is then also compact. So this is super useful. And one illustration of why this is useful, in particular, is the following example. Suppose I have a compact operator A, and I want to take 1 minus k, by which I mean the identity minus k to the n power. Right. As for example, if we're dealing with a solvent of something, then I can expand this as the sum over j equals naught to n of n factorial over j factorial n minus j factorial of minus k to j, that's the binomial expansion. And this is the sum. This is 1 plus the sum from j equals 1 to n factorial over j factorial and n minus j factorial of minus k to j, and find this as minus kn, and we guarantee that this guy kn is a compact operator. So now suppose I have some operator T that lives in a set of linear operators between H1 and H2. And this guy T is called finite rank if its range is finite dimensional. Key point here is that finite rank operators are compact. Seems like a lot of work to go through to make these definitions and work with these particular operators. But they're actually super important in the sense that we're going to come back to all of this stuff, having done all of the heavy lifting in this section, to talk about the algebra of operators. So we're going to find out a little later that with these properties, operators in particular, compact operators, actually bounded operators as well, satisfy certain what's called a C-star algebra, which with certain restrictions form a set of objects known as von Neumann algebras. Right? And it's these von Neumann algebras that allow us to classify observables in quantum mechanics that we're going to come back to. So this is a lot of heavy lifting, but it's heavy lifting because it'll save us a lot of work in the future. Yeah.
Then how we want to do complete, then like finite rank copies of content.
Because compact operators, where is it? Compact operators any bounded sequence in H1, right? So this guy is in H1, and in fact, some bounded sequence in H1, T will map this to some set of objects that have a convergent subsequence because it's a finite dimensional vector space. And hence, any finite rank operator is compact, but actually also any linear transformation of a finite dimensional vector space is finite rank and therefore is a compact operator. Okay. So now suppose I have some sequence of operators that is compact. So here's a set of operators Kn living in a set of linear operators between linear maps between H1 and H2. There's compact. And I've got some other K in set of linear operators such that the sequence approaches K in the sense that if I calculate the norm of the difference between K and Kn, then as n goes to infinity, this goes to 0, then the operator K is also compact. K must be compact. And I want you guys to show. That. K is compact. As, what do you guess? It's adjoint. Is also compact. Alright, but this is just the usual emission adjoint. So now I want to define possible operators that to come back to possible, especially in the theory of integral equations. And this is the idea of Hilbert-Schmidt operators. So to that end, suppose I've got some Hilbert space H. With off a normal basis. Goes down. Then the operator T or an operator T or a Hilbert Schmidt operator if space of T dagger T, so the T adjoint T. This trace recall in this orthonormal basis, I calculate the trace by computing the matrix elements of this operator T adjoint T, right, in that basis. So this is the sum from R equals 1 to infinity of EI. In the finite dimensional case, this is just the sum of the diagonal elements of the operator T dagger T. Okay, but more generally, that's what it means. T acts on this guy, and T dagger acts on this guy. So this is just a sum from I equals 1 to infinity of T E I in a product T I. And this is just the sum from I equals 1 to infinity of the norm of the state TEI squared. Again, I'm using this to define what a Hilbert-Schmidt operator is, right? This operator T is called Hilbert-Schmidt if this number that I get is finite. And as I alluded to earlier, these operators occur quite frequently in the theory of integral equations and have the really important property that they are, in fact, compact. So Hilbert-Schmidt operators finish off today's class with an example. And the example is one that we will see in the theory of integral equations. Now, if you first actually define what an integral equation is, this will define what an integral equation is. Right, so consider the integral operator K, whose action on some function or some vector in a Hilbert space U is defined as follows. Integral from A to B of K of X and Y. U of Y, W of Y, integrated over Y. And this is f of X. In this equation, K is known, it is our integral operator. Right, so I specify, remember, we talked about continuously indexing an operator. So this is an operator with continuous indices X and Y. So this plays the same role as the ij that we normally write to index the matrix elements of an operator, right? Now these guys are continuous. This guy is known, this guy is unknown, and this guy typically is known. This is just a wave function. Okay, so let's make this clear, and I'm going to use this to define what I mean by an integral equation. So this is a known, typically function. This is the wave function. So depending on what kind of integral I'm doing, if I consider it equal to 1, for example, or something else, depending on whether I'm talking about Riemann or Stieltjes or whatever. Right. So depending on the measure, this is just used to define the measure of the integral. Okay. This is what's known as the integral term. Right. And it is known to be. Right. So again, you've seen this before actually, in the context of, for example, Fourier transforms or plus transforms, right? The thing that comes that defines the Fourier transform, to the I dx, right? That's what this will be. Okay. Or the thing that defines the Laplace transform, or the thing that defines the exponential that defines the Laplace transform, or the exponential that defines the Fourier transform. You've seen other transforms, they also define by some specific thing, right? Fourier time, sine transform, cosine transform, cosine, cosine, all that. That's the integral right? And it is known. So if I tell you you're doing a Fourier transform, you know what goes in that pairs up with things in the integral, right? That's the integral term. It is known. Okay, I tell you what it is. This is a known function. It's the right hand side of this equation. This is the unknown. Right? And this is the thing that you're trying to determine. So you can see if you contrast what's going on here with, say, what you would do in a differential equation. So there I have some differential operator that acts on some unknown function. Give me some right hand side of the equation. And what do I do when I want to solve a differential equation? I integrate both sides of the equation. Right? Here, if I want to solve for this guy, then I have to differentiate it. But that results in a differential equation, which kind of hasn't really brought me anything useful. Okay. So what we're going to learn about quite a lot is how to use operator theory to solve equations like this. Right, so this is an equation, this is an integral equation. There are different types of integral equations depending on whether the unknown is just inside the integral or it's inside or outside the integral. That's first or second time, depending on whether these limits of the integral are constants or functions of x. For example, that defines different integral equations or Terra type or the classification problem that comes with these integral equations we will go through shortly. The point I want to make here though is just this is what an integral equation is. And I want to use the last, let's say 10 minutes to show you that the operator that is defined by this integral equation is a compact operator. Okay. So, in what follows, I'm going to assume that the weight, for simplicity, is 1. And that the Hilbert space we're talking about is a set of square integrable functions on the interval from A to B. Right, so that's it. I know that I can integrate these functions. That integral is well defined. We have one more constraint there, which is that K is continuous. The function of two variables, K of x, y, is continuous on the closed rectangle AB cos AB. And right, under these conditions, K is Hilbert-Schmidt. Right, and my claim is that it is compact. And to do that, I have to demonstrate that if I integrate the absolute value of K of x y squared, that interval on the two plane, that is finite. Okay. The claim here is that A is compact. So firstly, since I've already assumed that K of x, y is continuous on this interval, since K of x and y is continuous, the integral, double integral, it could be a to b of mod x y. Sorry, thank you. It's stronger. I'm going to say that this guy is overshot. So I already know that this integral is finite. First case, continues from that. To show that it is Hilbert-Schmidt, I have to demonstrate that this trace is finite. Okay, or my continuous variables. So the trace of K dagger K is the integral, sorry, the sum over I equals 1 to infinity of EI K dagger K. And I need to put this into an integral form. So to do that, I use the fact that on the set of square integrable functions indexed continuously by x or y, that I have a resolution of the identity, namely that if I integrate x out of product x, so ket x, product x, dx, that's one. Okay, so I use the resolution by NP, yeah, to insert between between E and K dagger, between K dagger and K, and between K and E. Right, so it's a sum over I, and then an integral. Technically, it's a triple integral, but I think you all understand that. Of EI x x K dagger y y K z z then E I. Okay. So all I've done is use the fact that the integral of x and the same for y is z dx is the identity. That's the resolution of the identity that comes from the fact that our Hilbert space is square space of square integral functions. This guy here is just A of x, y conjugate. This guy is K of y, z. And I can rearrange these guys, this one here and this one here, and move them together. So this is sum, or rather the integral of K of x, y conjugate, K of complex function, sorry, K of y z, and then I have sum over I equals 1 infinity of z EI x. That's what it is. I took this guy and I moved it to the right of this guy. Right, and now I'm summing over the EIs here, and I use another resolution of the identity between EIs and a continuous variable z. This just produces for me the Dirac delta function, Dirac delta distribution, z minus x, and then I'm integrating over x, y, and z. Okay. When we discussed the Dirac delta distribution, all of this stuff was put in the question.
The EIs, the summary EIs are a complete basis.
That's right.
I'm just confused, like, because we've got a continuous basis.
Correct.
And discrete one.
Yes.
Does that not have a problem?
It does in the sense that when I take this sum here, it doesn't produce a Kronecker delta, it produces a Dirac delta, right? Because it's specifically because it's continuous variables.
Well, we can express it discrete basis.
That's right. In terms of distribution. And so I'm going to need to what the wall space I have there to finish this. So I'm talking. So this is the delta. So now what I have is a sampling function right? Which if I integrate out over z, is going to sample everything that involves z at x. Okay, so I do the integral over, I'm now taking care of the sum, and I do the integral over z, and that says, the Dirac distribution says, replace in everything that multiplies this, replace z with x. So what do I have? I have the integral. Now let me just insert HB. K complex conjugate of x, y, k of y, x, y, x, x, y, doesn't even matter. Dx, dy. But this is precisely what I would call mod k of x, y squared dx dy. We just said that because this is a continuous operator of a rectangle, it's finite, therefore s of k is finite, therefore k is a Taylor-Schmidt operator. Okay, so next time I will define for us the spectrum of Taylor operators, and we will move towards the spectral theorem of the combined operators.